If I can click the button, yeah. Welcome everyone to our talk on RTX Mega Geometry. Before we get started, a few reminders. If you have mobile phones or other sound-making devices, please set them to silent so you just don't disturb anyone. And a reminder that there's an evaluation. So after the session, please fill out the evaluation so we can get feedback on the talk. Okay. So myself, I'm Jan Schmid. I'm a senior manager on the RT Core team at NVIDIA, part of the driver team. We do things like the Mega Geometry API I'm presenting. And a short overview over the talk. First, I am going to talk about clustered BLAS and partitioned top-level acceleration structures, which are the two features Mega Geometry consists of. My part is going to be a little dry. I apologize for it. I'm from the driver team. Afterwards, you're going to have a lot of really nice pictures from the applications that my colleagues Adam and Juha are going to present from Zorah and Alan Wake 2, respectively. So even if you struggle a bit to follow on the API side, because yeah, it's a bit dry and I don't have that much time, please stick around to see all the great images that are coming later. Yeah, so first of all, what's wrong with ray tracing right now? Why do we doing this big change to the ray tracing API with Mega Geometry? To summarize it fully is I've seen a lot of other talks now, and a lot of games don't really put the same geometry in their ray tracing environment as they actually rasterize. And that's a bit of a problem. It's painful to work around. It also means we can't ray trace primaries. And the ray tracing effects just don't look as good as they really could. Why don't they? I list 3 reasons, and these are the ones we're trying to address to get games to really put the same content into ray tracing they use for raster. The first is high geometric complexity. I use an example here from Zorah that Adam will present later. If you have this amount of geometric detail, you often have some seamless LOD solution or something, which results in a lot of BLAS rebuilds. Or just very slow BLAS build times. So games would kind of accommodate this by replacing their geometry with proxies or other lower detail versions, which is not what we want. Then you have large instance counts, like in the Electric Dreams demo by Epic, where you have millions and millions of instances. Your TLAS build times become really slow. So you just kind of call instances in the distance. Now your reflections, you have to use other solutions to get good reflections, so on. It's like your path tracing doesn't work. Yeah, not great. For which we'll use Partitioned TLAS to try to address this. And then high animation cost. If you have a lot of animated meshes in your game, then really refit cost can quite quickly become a bottleneck. And then you might reduce the frequency you're doing your BLAS refits, or other ways to kind of mitigate this, or just not have some of your animated geometry in the ray tracing world. So we're also trying to speed up the refit performance for animated meshes. So first I'm going to go over clustered BLASs. So clustered BLASs are really about this new object type we're adding to the ray tracing API, the cluster level acceleration structure, which will represent a small grouping of triangles. And out of these CLASs, you will then construct a BLAS. We call this BLAS a cluster BLAS, but for most intents and purposes, it will behave the same as any other BLAS in your title. These CLASs don't have any extra transform layer, compaction, or refit. So they're much simpler than what you'd have in a BLAS. And they're limited to 256 triangles and vertices, just like what you'd use with a mesh shader in the worst case. Since it's important that when you construct these CLASs that they're compact and not spread out over the mesh so that they have pretty good SH properties, we allow you to assign geometry and illicit geometry flags for each individual triangle, because we don't want you to split your mesh when you split it into clusters based on non-geometric properties. We really want you to be able to have your material go anywhere in your CLAS. And finally, we don't allow the CLAS to be added to TLAS directly, so traced, so you have to first create a BLAS out of it. And this allows us to strip out a lot of extra information needed for tracing, so CLASs can be as small as possible. So here you can see the bunny Yeah, I don't have the sexy picture, sorry. Here you can see a bunny that is clusterfied, and you can see that the clusters, if they're good, really align with this kind of boxy shape you'd expect from like axis-aligned bounding boxes. So when you trace a clustered BLAS, there's a few small differences with the BLAS. First, your primitive index will refer to the primitive within the CLAS. So primitive indexes will not index within the whole BLAS, but within the CLAS the ray hits. And now this leaves you with, oh, I don't know which CLAS I hit in my BLAS. So that's why we added the get cluster ID intrinsic. Here you can retrieve a 32-bit user-defined value that you've provided when you construct the CLAS. So it's up to you what this value means. But we expect you to somehow use this value to fetch your vertex attributes or other data you need when you hit an object in your scene that you normally use your BLAS and primitive index for. If you call this intrinsic and you've hit a non-clustered BLAS, so a more traditional triangle BLAS, we will return a predefined value, so you can use that to check whether you've hit a cluster or not. And to reiterate, yeah, the overlap, like the way you construct these clusters is really important for trace performance. The way you would usually do this kind of for mesh-based rendering is more based on circumference of a mesh for like good occlusion culling. This works for ray tracing, but ray tracing would prefer more boxy shapes like in the pictures, so to optimize for the SAH of the clusters. So how you construct the CLASs. So here's an example, pretty straightforward. So in the regular case, you have some indices, optionally some geometry indices if you assign per triangle geometry indices, and vertices, and you build a CLAS. But then we also have a completely different path to construct CLASs. We call this a cluster template path using another new object called cluster templates. You build these from just indices and geometry indices, again, also optional. And then you end up with a cluster template object. And then you can instantiate this cluster template object to create a CLAS. So in this case, I end up with exactly the same CLAS in both paths. Just if I use a cluster template path, I have this intermediate object. Now, why would I do this? That's because I can now also assign different vertices to the same cluster template instantiated with a different set of vertices, and you will get a new CLAS B, which has the same topology, same geometry, but different vertex positions. So, and this instantiation path is much faster because you can cache all the topology processing we do in the driver. So applications for clustered BLAS. A few more things. Sorry about cluster templates. So these are basically like a CLAS, but don't contain any positional data. So of course you can't trace them, the vertices in them. They exist as vertices, but don't have positions. And they can be instantiated many times with these vertex positions. So we use this to replace any refit functionality. So we don't provide a refit for CLASs. Instead, we expect you to create a cluster template and then instantiate that, for example, for animated meshes. We can offer fairly close to memory bandwidth performance when instantiating CLASs in this way. And this is one way you can get much higher refit or rebuild rates for animated meshes by using this cluster templates rather than the traditional BLAS refit. Another use case that you see in the picture is to use it to implement tessellation. So you just create cluster templates for different tessellation patterns, and then you instantiate these, you run your own kind of tessellation processing compute shader, and you choose where you need this tessellation patterns with what vertex position, and you instantiate them. And this actually works really well. If you've seen the Dragon demo we showed off in optics, this is basically how that works. Now I get even more boring and dry and talk a little bit about the API, but just try to go over it relatively quick and to just give you an idea on how this works. So we have for clustered BLAS 2 function calls we add to NVAPI. The first is pretty analogous to pre-build info. So it's to get the requirements. The text is really small on this laptop, unfortunately, so I have a hard time reading. But as is expected from a kind of pre-build operation, you have a max kind of R count. This is the maximum number of CLASs you're building if you're building CLASs. The same operations also support building BLASs and building cluster templates. So it's just a different enum value for the different kind of object you're trying to build. So the max R count is just the number of objects, the max number of objects you want to build in an indirect way. The flags are just build flags, not that exciting. Then we have the type, and this is, as I said, is like what do you want to do in this call? You can build BLASs from CLASs, CLASs from triangles, cluster templates from triangles, instantiate cluster templates, or we allow you to move any of these cluster objects. The move is analogous to an STD mem move, so it's not like the original object gets invalidated, but the destination can overlap with the source. So you basically provide an array of source and destination pointers, and the destinations can overlap any of the source pointers. The very obvious use case for this is implement your own defragmentation, which we found you have to do probably sooner or later if you have a lot of CLASs, and this really makes this much easier, and we can provide a driver-optimized operation for this. Then the mode, there's 3 different modes. The first is implicit instantiation, which I'll kind of use in this example. Here you will provide a single buffer to the call, in which the driver will then allocate the result objects for you and then return the pointer to the resulting objects. We have an explicit destination mode where you will provide a pointer for each individual object. The driver will just construct it at that location for you. And then we have a get sizes mode, which is kind of a way to on-device fetch the size of every result object. So this is meant to be used in combination with the explicit destination. So in a compute, you first fetch the size of all the objects, then you run a compute shader that determines where to allocate the objects, and then you run the explicit destination. If you don't want to go through all that, you can just use implicit destination and you get a single linear buffer that is allocated. The driver will allocate for you. And yes, because in this case, we're doing building CLAS from triangles. In the union, we use input triangle desc. And yeah, this is sort of what you expect from pre-built info. So you provide the vertex format so the driver can make a good kind of guess on how large the objects will be. And then a lot of max values. Perhaps one interesting value is the min position truncate bit count. So we allow you to tell the driver to truncate a certain number of bits from the floating point numbers to compress. You don't have to manually set these to 0 or anything. You just tell the driver, okay, just drop the last 5 bits of all my floating point numbers, for example. And for the pre-built info, you will specify the minimum number of bits you will drop for any object in the call to reduce the memory of the pre-built info estimate. But then later in the call, you can drop different number of bits for every individual build. Most objects don't need 32-bit floating point position, and this is especially useful if you're doing animation or something, and you don't want to manually zero out the bits for our compression to do its work. And then, as you'd expect from pre-built info, you get the requirement info out, which will tell you the max memory needed. In the implicit case, this is for the total allocation for like the whole batch. If you run it in explicit mode, this would be for each individual object because you will have to allocate each individual object separately. And then the scratch size, which regardless of mode is always the total scratch size needed for the whole call. Okay, now you can allocate this stuff, and now you can actually call the multi-indirect build call. So we have the desk, and the first member of the desk you'll pass is probably the same input struct, at least the first time you implement this. You can have an input struct that has lower values that result in lower memory consumption than what you ran pre-built info for, but you can't have any values larger. One of the reasons we pass this in here is validation can pick up if your buffer is too small and immediately throw an error, rather than us just stomping your memory and you not really knowing what's happening. Yeah, and then the other members here, I really cannot read, but the address resolution flags, I'll skip over. Actually, maybe I can move this a bit larger. So the batch result data, you will return if you run implicit mode, like the pointer with the full allocation, and then the batch scratch data, the pointer with the allocation for all the scratch data. So these are pretty obvious. The destination address array will change its behavior depending if you're implicit or explicit. In implicit case, you provide an array of pointers, and the driver will fill it out with the address of all the results. In explicit mode, you also provide an array of pointers, but you're expected to already have a pointer in them, and the driver will read the pointer from this array from where to construct the object. Then the result size array is optional. You can provide an array of UN32s, and the driver will tell you how large each object was that you just built. Very useful if you then have to do some kind of compaction or memory operation immediately after this call. The indirect arg array is where the magic happens. So here you will provide a device-side array of these structs with the parameters for each of the objects you want to construct. As I mentioned, we're building CLASs, so you provide the cluster ID, some cluster flags. Then it gets a bit more traditional. You have the triangle count, vertex count, and now this position truncate bit count, which is, again, how many bits you want to drop from all the floating point numbers. The index format, which you can change for every object since it doesn't affect the memory consumption, really. And so on. You can see also we support OMMs right at the start, so you can assign OMMs to clusters. We'll work out of the gate. Another member maybe to highlight a little bit is this geometry index and flag buffer. And the base geometry index and flag, we pack the geometry index and geometry flags together in a 32-bit value. And you provide a base value that is applied to all triangles, and then an optional buffer where you can provide per triangle values. Then for the geometry indices, we add the two together, and for the flags, we OR them. This way, if your whole cluster is uniform, you have the same flags for everything or the same geometry index for the whole one. You don't have to allocate a whole buffer with values. You can just use the base one, and then you can use the buffer to kind of like modify that for individual triangles for clusters that need it, just so you don't have to allocate all this memory and deal with this. Yeah. And then we get some clusters out. So the destination array will have all of the CLASs after this build call. Now we need to actually build BLASs out of this, and now this is pretty much the same. So we already went over this, except we built BLAS from CLAS now, but we still use implicit destinations, input type CLAS now, so you use the other union member. And now you, instead of specifying the max triangle count and so on, you specify the max number of CLASs referenced by each BLAS and the max total number of BLASs your entire call has. This being split this way is very useful because often you're in the case where you build a max of like 1 million CLASs, and then you build a max of like 10,000 BLASs out of those, but you don't know how they're distributed. This way you can do this because there's a max total amount of CLASs, so the memory calculation can actually give a very reasonable upper bound to the memory consumption, even without knowing how the CLASs end up distributed across all the cluster BLASs. And then you get the same requirements info back out. And then we actually do the call to do the multi-indirect dispatch on the command list. Inputs, again, the same. This time, the cluster, the indirect args, you use a cluster args struct on device, and you fill out essentially an array of CLAS pointers, which is a cluster VAs field. So each cluster BLAS you create is created from an array of CLAS pointers, which are then referenced by this cluster BLAS. So yeah, you reference all your CLASs, and then you get the BLASs out, which will then reference those CLASs. So the BLASs will be much smaller, because they only contain references to the CLASs. Of course, if you then delete or remove the CLASs, the BLASs will become invalid. Yes, and that's the cluster part. Now, quickly, I'll also talk a bit about the partitioned TLAS. This is about helping with the many instance case. You can see that one of the samples we have on the left here, where there's some dominoes on the plane, this is colored by which partition is assigned to each of the instances. So the instances are colored by its partition, so you can see these squares. This sample uses a simple grid, but you could use an octree, a quad tree, or like any other way to assign partitions to instances. This aims to solve the many instance build time issue, and it is based on the assumption that most instances are static most of the time. So yes, any individual instance might be modified, even one that's usually static, because you might have destruction in your game. But most of the time, instances just sit around and do nothing, and then, maybe they get active. And some instances move all of the time, but most instances are generally static. And we want to avoid rebuilding all the static content in your scene every single frame, because it really is dragging us down. So the partitioned TLAS adds a new monolithic data structure as an alternative to the TLAS. It is constructed from an existing partitioned TLAS and a series of modifications. So the partitioned TLAS is like stateful in effect, in that like all its contents will stay there until you modify it. So you do this through a series of device-side operations, each with a series of an array of arguments. So an operation might be change this instance or change this partition, and then the arguments would be how you would change all the instances or partitions. And it is optimized to do these updates, but you can also do these updates in place, so you don't have to like copy to a new destination all the time. Of course, you can do these updates in place, in which case we only do the modifications needed. This really relies on your game being able to express changes between individual frames as deltas. If you keep having to figure out what changed between frames because you reconstruct everything, I think you have some work to do to really be able to leverage this, but it's very beneficial once you are able to do that. During trace, the partitioned TLAS will behave exactly like a regular TLAS. There is no real way for the app to detect if it is a TLAS or a partitioned TLAS during the trace. How this looks from a geometric level, the instances in the partitioned TLAS is, like the name implies, grouped into these partitions. Partitions are also not an extra level of hierarchy, so they don't support any reuse, so you can't have the same partition appear more than once. It will appear exactly once, and each instance will be in exactly one partition. We do support translation on the partitions, but it is basically baked in the partitions when they're built. The trace performance is also, just like from the CLAS case, affected by the spatial overlap of these partitions. So you want to make sure the partitions don't really overlap each other, are as spatially distinct as possible. So grids work, octrees, quad trees, those kind of structures work. More semantic scene hierarchies can produce pretty bad trace performance. So we would not expect a partition to be like a car or a house, because that would overlap all the objects. Instead, it should be spatially distinct and more spatial segregation. If you change things, the build cost will be relative to the total amount of instances in a partition you're modifying. So if you're changing one instance, you will pay a build cost somewhat comparable to the instances in that partition. And there's an additional cost based on the total number of partitions in your data structure, because it has to like tie these all together in a big BVH at the top. So as an app, you should kind of balance the partition size based on your needs. A recommendation based on our investigations is somewhere between 100 or 1,000 instances per partition works pretty well, because you get like all the benefit of much faster build times without the partitions becoming so large that if you decide to change it, you get this spike in performance. Like if you have huge partitions, you have to change something, get a huge spike. And your build time is not really better because partitions of a size 100 is already, at least on paper, 100 times faster. So that's probably good enough. Then the data structure and how memory works. So pre-built info, the PTLAS memory is only based on the max instance count and max partition count. Actually, they're fixed. It is always just, this is the instance of partition count of the PTLAS. The number of instances within partitions or the max does not affect the memory consumption of the partition TLAS. So the partition TLAS will use the same amount of memory whether all instances are in a single partition or each instance in its own partition, but the maximum number of partition and instances you have will affect the memory consumption. And the instance partitions are all persistent and indexed, so all the operations access them by their index. There's a partition index and an instance index. And you could choose just which partition your instance is on. Based, it has the instance data has a member partition index. So if an instance should move from one partition to another, you just change that instance and give it a new partition index, and then we take care of all the rebuilding necessary to make that happen. Then one more thing about the partition TLAS. We have one feature that's worth highlighting. So there's a special partition index you can set to instances, which will move those instances to the top level of the top level acceleration structure, and make them behave as if they were each in their own individual partition. This is intended to be used for things like actors or characters roaming around in your game. If those move around across partitions, you'll have like these partition rebuilds event happening all the time. Not really that beneficial. That might be fine for destruction or other occasional changes, but like an object that moves all the time is not worth invalidating partitions all the time. So you can just put an actor or a bullet or something like that in these global partition, and it will just be tied into the build every frame, just like you would expect from a normal TLAS. You do pay some trace performance cost for this, but the assumption is these objects, since they change every frame, the small trace performance cost, especially if they're small objects, would not be that much of a concern. Yeah, and then some samples. So all these APIs are available in a Vulkan extension and an NV API. I have some QR codes. I think the top one is to the NV Pro samples in Vulkan. The bottom one is to the NV API sample RTX MG. So you have an animated cluster sample, which shows how to do like skinned kind of animation with clusters with template instantiation. Tessellated clusters, where how to use template instantiation to implement tessellation. LOD clusters, which is like a nanite-like LOD system implemented with clusters. RTX MG, which does tessellation as well, but in NV API. And then a sample for the partitioned TLAS, which is this dominoes example I showed earlier. And next up, I hand over to Adam, which can wow you with amazing pictures.
All right. Thanks, John. So, yeah, I've got all the goodies. So if you haven't seen Zorah, I'm going to show you some images from Zorah. Zorah is our CES demo that we showed when we announced the Blackwell line, 50 series line of GPUs. So here's an image of our start screen. This is RTX Mega Geometry working in Zorah. It is available now in our NVRTX branch of Unreal Engine. This is branched off of 5.4. So what did we do? One of the coolest things we did was trace all sorts of stuff, including primary rays. So we traced primary rays, shadow rays, reflection rays, GI rays, all the rays. And our BVH contained both clustered BLASs for nanite meshes and regular BLASs for non-nanite meshes, things like characters, lower poly things as well. And as Jan talked about earlier, the nanite meshes use cluster-level acceleration structures for their clusters. And a small bit about how this works in Unreal Engine, those CLASs are built from decoded nanite page clusters on stream-in. So as nanite is bringing geometry in and out of the engine, we go ahead and turn those into CLASs, cache them in VRAM, and then do a bit of GPU defragging so that we keep in sync with the nanite streaming manager. And so we do this every frame where we need to. We build the CLASs on the fly, and then we build clustered BLASs from them. And we do this for all of the static nanite meshes in Zorah. And just some numbers for context. In Zorah, we don't have a ton of instances. We have about 17,000 nanite mesh instances, which are clustered BLASs in Zorah, but we have a lot of CLASs. We have anywhere from 2 million to 7 million CLASs, depending on what you're looking at, what resolution you're running at. And ultimately, this results in anywhere from 350 to 850 million triangles in the BVH at any given time. Which was really amazing that we got that much geometry in. Here's a quick example. May not seem all that special. I'm looking at the ceiling in Zorah. And here is a visualization of mesh normals. Nanite has this concept of proxy meshes. These are low quality, low geometric quality meshes that the engine will use in ray tracing. We see a lot of limitations with these proxy meshes that we would like them to be a lot higher resolution. And with Mega Geometry, we can achieve exactly that. So here's the visualization with Mega Geo on, and I'll flip back and forth, and you can see the differences. So how do we make this happen in the engine? We have a customized nanite hierarchy traversal that's implemented in compute shaders. That's tailored specifically for ray tracing, but we could also use it with the rasterizer as well. And as Jan mentioned earlier, in order to get rid of the geometry mismatch that happens, we match the nanite LODs exactly with what the rasterizer would select, and then we can rebuild our BLASs on the fly. And so no more need for large bias values or missing contact shadows or anything like that. So one of my favorite examples is this. This is an image from Zorah. The primary rays and the primary color and things you're seeing here, it's all from ray tracing. This is not rasterized. And here's some proof. These are the intersected triangles from the primary rays with Mega Geometry turned on. This is what it would be if we use the proxy mesh geometry instead. So if I switch back and forth, you'll see the density of the geometry is quite a bit different when we have Mega Geometry. So other use cases, ray trace shadows was next on our list. Contact shadows are a great way to use Mega Geometry here. So here's another mesh normal visualization. This is of the nanite proxy mesh, and this is with Mega Geometry turned on. So all the high frequency detail is captured now, and we can use it in ray tracing. So here's a lit version of that same shot. This is with the proxy mesh. This is with Mega Geo. So for those of you in the back, you're probably like, nothing changed, right? Take a look at the slides and the recording afterwards. It will become very obvious to you, the difference. Some of the contact shadows in the proxy mesh version are just entirely gone. They're not there at all. Some shadows are just the wrong shape and stuff. So I encourage you to take a look closer. Okay, in addition to contact shadows, we have indirect soft shadows and ambient occlusion. Here is an example of the proxy meshes. Foliage is really tough for the nanite system to decimate down into a smaller, less complex mesh that is also representative of thin geometry. And so a lot of times that geometry just disappears and isn't there. And as a result, when you're ray tracing things like shadows or ambient occlusion, that occlusion just isn't represented anymore. And if you can have the correct geometry in there, the occlusion signal that you'll get is completely different. And it results in an image that has a much more depth. Okay. So out of Frustum content, we handle a little bit differently, and we scale the LOD down. This is part of the customization for ray tracing. We don't use the exact same LOD that you would use in the primary visibility, because for a lot of these things, you're not viewing them directly. So the first stop there is ray trace reflections. So this is a shot from Zorah. We're looking into a mirror in this shot, and there are a few spots. This is with the proxy mesh turned on. There are a few spots where the proxy mesh decimator doesn't get quite right, the geometry, and the geometry that the art team made is ridiculously detailed, and we're really missing out on that here. So if we turn Mega Geo on, hopefully even in the back, you can see that the result is quite a bit different and much more what the artist intended. Here's another spot. The difference here will probably be harder for some of you to see, but the geometry is much more faceted and jagged with the proxy mesh, and full quality exactly as the artist built with Mega Geometry. Another example here is where foliage doesn't come out quite right in the proxy, and in some cases it disappears entirely. And with Mega Geometry, we can bring it back. So not only does it appear in the reflection, but then occlusion and other ray trace elements of the light transport can then be correct as well. All right, and of course, GI. We talked about this earlier today when we were talking about path tracing nanite and Zorah. Here's an example of lumen. So lumen GI plus lumen reflections. And there are some areas here where occlusion isn't where you would expect it to be. And we can bring all that back with the correct geometry in the BVH. And there are other areas like this one here where the indirect light isn't represented in a mirror the way that it's represented in a primary view. And with Mega Geometry plus advancements in light transport, like restir and restir PT, we can then bounce rays off the right geometry and create an indirect lighting signal that is really robust. So on the UE5 side, the code that we wrote and the content that we built for Zorah is now available. So if you are curious how this was done in Unreal and you use Unreal, you can go pull the code right now. The link is here. QR code is here too. This is part of our NVRTX branch, our NVIDIA branch of Unreal Engine. The code release here is experimental, so just keep that in mind. It's not quite ready for you to go and ship a game tomorrow with it, but it is ready for you to experiment with, learn about how your art workflows would work with it. On the code side, all of the code for these two features, the clustered BLAS and partitioned TLAS, are wrapped in defines. So if you search for these defines, you'll find everywhere in the engine where we made changes, and you could also use these defines to compile the functionality out. The content samples are available on the Unreal Engine Marketplace soon. Also, if you didn't get to see the talk this morning where we talked about more details in terms of how the light transport and Mega Geometry are implemented in UE5, go look up this talk or the recording for this talk, and you can learn more. So here I will hand it off to Juha to talk about Alan Wake 2.
Okay, yeah. So hello, I'm Juha from the NVIDIA DevTech. I've done quite a lot of work with Alan Wake 2 RTX features, and now I'm going to talk about how we applied the Mega Geometry clusters to the game. So Alan Wake 2 released over a year ago with path tracing. The ray tracing PVH in the game was especially challenging. The game environments contain these large and detailed forests. The levels are open-world-like in structure, with large playable areas with wide exterior spaces. Object count is very high. The forests are dense with layers of vegetation, grass, bushes, trees, and so on. A large part of this vegetation is animated as skinned meshes, which are then represented as dynamic BLASs in the PVH. Instancing is used to reduce the number of BLASs with unique position data as much as possible, but despite that, there is a lot of BLASs to build every frame with lots of animated vertices. Also, the lighting setup is demanding. Many scenes have this difficult low-angle sunlight where shadows from faraway objects can't be visible. And because of the open world-like structure of the levels, the view distance can be long. In some areas, you can see entire forest landscape moving in the wind. This means that culling of instances from the TLAS didn't help much here. In the original game release, the solution to keep the BLAS building at reasonable levels was to limit the rebuild frequency based on distance from the player. The view distance was split to cascades, and near the player, everything was updated every frame. And then on the areas at longer distance from the player, the game starts to skip the rebuilds. And because of the G-buffer is always rasterized, so this is kind of a hybrid renderer, the skipping of BLAS updates doesn't immediately become visible, but it however means that G-buffer and the PVH don't completely match. In the distance, the PVH doesn't accurately follow the vertex animation. And while this overall this works like reasonably well, it still causes some visual issues, and it is still heavy on both GPU and CPU. So a original solution wasn't like a completely satisfying and required some compromises to be made. We wanted to try the Mega Geometry clusters on this problem. Not only the dynamic BLASs were problematic, so the static content is still triangle-based. Using clusters, it requires splitting the original geometries into clusters. The chosen clusterification method, it affects especially the ray tracing performance. The game uses mesh shaders in rasterization, and for this it splits the geometries into meshlets. And at first we tried to use these meshlets as clusters, but eventually we turned out that we get substantially better performance with a solution that's designed specifically for PVH building. The method that we used and gave the best performance in our case is now available in GitHub as a small library. The image on the left here is a visualization from the Alan Make 2 clusters from Nsight Graphics Capture. The latest version of Nsight is compatible with the Mega Geometry, and it allows you to capture and inspect the clusters. A basic parameter in clustering is the cluster size in triangles. After some experimentation, we ended up with max 64 triangles per cluster. This gave the best performance for us when counting both the PVH build cost and the ray tracing performance. The API needs the max size to be defined from the CPU for each cluster operation. So the fixed max size allows handling of all clusters from all meshes with the same operations. The game uses 16-bit site normalized values to store all vertex positions in object space. So site normalized with values between -1 and +1. And because of this limited precision, we could safely apply the bit truncation available in the API to get a little bit extra performance. The skinned vertex positions are written out each frame by a separate compute shader pass that feeds both the mesh shaders and the PVH. And even though the meshlets and the clusters, they are not the same vertex positions can be still used. So to build all the dynamic BLASs in the game, at most 3 cluster operations are issued from the CPU side each frame. First, we check whether any new meshes have been loaded from the disk by the streaming system, and if so, cluster templates are built for those meshes. The template arrays are shared when possible. When the opaqueness status of the mesh is the same and the used opacity to micromap is the same, the template array can be shared between 2 different materials of the same mesh. Skinned positions from first use case are given to the template creation for optimizing the template. This possibility helps a little bit with the ray tracing performance. These template arrays, however, they need to only be built once, so in case no new meshes have been loaded from the disk, this operation can be skipped. The second cluster operation is template instantiation. Reinstantiation with new positions happens on every frame, regardless of how the vertices have moved, so we don't track the movement. All clusters from all meshes are handled with this one operation. The third cluster operation rebuilds BLASs from the instantiated clusters, and again one operation to handle all the BLASs. For each mesh with unique positions, the clusters and the BLAS reside in the same memory allocation. This allocation replaces the allocation made for a triangle BLAS when the clusters are not used. All these operations handle all meshes in independent allocations at once. The explicit destinations mode in the API is used to manually direct the writes or the output to these independent allocations. Also, all these cluster operations need some scratch memory. The operations are separated by the UAV barriers, so the scratch memory can be shared. and it can be also shared with TLAS construction. And because the TLAS build, it usually requires the most scratch memory, the cluster operations don't actually need any additional memory. The cluster argument or the cluster operation arguments, they must be given in one big array in the GPU memory. And for all of these or each of these operations with targets the many measures in independent allocations at once, that array needs to be filled based on what measures are built on that frame. To do this, the information on CPU is uploaded and expanded with one computator pass for each of these 3 operations. The clusters created from the same mesh, they share many arguments needed in the template or the cluster arguments, or the values can be trivially evaluated based on the cluster index. Here's an example on how the PVH build flow looks on GPU timeline as captured by Inside Graphics GPU trace. This location here has about 2,000 skinned cluster BLASs with about 100,000 clusters and 5 million triangles in total. The argument generation at the front is very light. The cluster instantiation takes most of the time, and BLAS building a little bit after that, about 1 millisecond in total for the dynamic BLASs before the TLAS can be built. These cluster operations handling all measures at once, they fill and utilize the GPU more efficiently than equivalent triangle BLAS build calls would do. Since the cluster operation arguments are generated on GPU, it's relatively easy to skip rebuilds of cluster BLASs when a given BLAS has not been hit by any rays on previous frame. The hit information doesn't have to be read back to CPU at any point. All hit shaders have one extra line of code for increasing hit count on the instance. Before the argument generation, the instance hits are mapped to BLASs, and then BLASs without any hits are skipped when writing out the arguments. This saves about 20 to 30% in BLAS build cost when being outdoors in the forest. It saves a bit more when being, for example, inside buildings, but being outdoors in the forest is it's an important worst case scenario. Triangle BLASs are still used for static content, so there are both cluster and triangle based BLASs in the TLAS. So when hitting a cluster BLAS, because BLAS, the preventing index means triangle index within the cluster. When hitting a triangle BLAS, it means triangle index in the geometry. And there's a new data field, cluster ID, and it's used to resolve this. The base triangle index in the geometry is stored in it for the clusters, and this is set in the template arguments. The cluster ID intrinsic function, it automatically returns -1 when a hit is on a triangle BLAS, so this has to be taken into account. There's some performance comparisons between triangles and clusters. Here's the memory consumption. There are some differences between hardware generations in the memory usage, but these numbers, they have been measured on Blackwell. The cluster BLASs don't require the separate scratch memory for each BLAS to support the building, and this in effect reduces the total memory consumption with clusters to less than what is used for the triangle BLASs. Memory management is done for the clusters based on the CPU side estimations, and the API would offer the possibility to read back more accurate sizes back from the GPU and optimize the memory consumption even more, but we didn't use that here. The biggest performance improvements are seen on the CPU side. The cluster implementation is single-threaded, but the triangle BLAS building uses multiple threads. The bars shown here are the total CPU time consumed by all threads doing the work and the slowest individual thread. For the single-threaded clusters, those are the same. The cluster-based implementation is very light and could likely be optimized more if needed. But even this basic implementation more or less eliminates the CPU side workload. With triangles, the performance is a trade-off between CPU and GPU. The work could be distributed to more threads, but that would happen at the cost of GPU performance. When many tiny triangle BLAS build calls are made on the same command list, the driver has some opportunities to patch them and run them in batches with better efficiency. So using more threads and command lists can prevent this driver-side patching. And here are the GPU performance numbers. On the top of the raw numbers without using async compute, and then below are practical numbers with async compute enabled. The PVH building is substantially more efficient with the clusters. As Alan Wake is a hybrid renderer using both rasterization and ray tracing, it's possible to overlap the PVH building with gbuffer and shadow map rendering. This hides some of the PVH build cost, but not all of it. And anyway, the ray tracing performance passes are a bit slower with the clusters, but even when the async compute is used, the win in the PVH building is usually bigger to turn into overall perf improvement also on the GPU. So overall, the Mega Geometry clusters allowed us to do something that was not possible to do before in Alan Wake 2. We could build the complete forest PVH without skipping any BLAS updates. When using the clusters, it matters how you do the clusterification, how you split the meshes into clusters. For optimal ray tracing performance, a method designed for PVH building should be used. Setting up the cluster-based BLAS building, it requires a bit more than a trivial triangle BLAS implementation. But when you have to start doing tricks with the triangles, like skipping the updates or fine-tuning the multithreading, you could as well switch to clusters and get better performance with similar effort. And you can of course combine the different options, like in Alan Wake 2, use triangle BLASs for optimal ray tracing performance for static content where the PVH build cost doesn't matter, and then use clusters for the dynamic content where the PVH build cost is a problem. But that was everything for me and everything for today, I guess, unless there are questions.
Listen, out in the dodge. Do it on a call. Very good. Thank you.
Please, if you do have questions, come to the mic to ask questions.
You got. Oh, no PR outside.
We will also be outside after this, if you wanna rather ask there. Okay, that's one.
Hey, hi guys. Very nice presentation, and just had a quick, recap, just to make sure I understood things properly about the clusters. So we can do 256 vertices and indices per cluster. Is that correct?
That's correct.
Okay, so not more than that. Is that because it's indexed in that way, or it's a hard limitation, right?
And it's about it's hard.
Yes, that's a hard limitation.
Okay. Is there how many clusters per BLAS can we have?
Hello.
2 to the power of 28.
Okay, that's plenty. Okay, that sounds good. And now the partitioning. So you guys said there is it needs to be spatially partitioned for performance reasons, but it's not that bad if we have like small geometries, because only if it's small in the screen, it's not going to be that much of an issue, right?
You can imagine it depends on like the size of the overlap. Effectively, the more overlap, the worse.
Yeah, makes sense. Okay, and those partitioning can be updated individually, and that's the whole point of it, right? So like you don't update everything.
Yeah. So the driver doesn't need to know your partitioning. The driver just needs to know which partition each instance is assigned to. The partitioning is what you use on application side to assign partitions to instances.
Okay, and if we have a moving origin, do we still have to update everything, or is there a way to like add in some kind of offset?
We have this special partition translation feature, which I didn't go over in the slides, but it is kind of an extra fast refit for the entire data structure.
Okay, so there is a way.
It's still somewhat costly due to how things work, but it
it's
is
cheaper
faster. It is cheaper than what you can do today.
Okay, perfect. Thank you.
So I have two questions regarding floating point precision, and I guess part of it was addressed in the last answer. But I'm wondering first, I know the guidance for large scenes in the past without Mega Geometry was to place the world origin at the camera to maximize precision. And I'm wondering with the Partitioned TLAS if that's obviously still possible, but is it necessary at all if you have this additional layer in the BVH? And presumably, if there's transform there, you basically have 64 bits of floating point precision. And my second question is, NVIDIA has a blog post with guidance for avoiding self-intersections for shadow arrays, and there's some magic constants there for NVIDIA hardware. And I'm wondering if the same thing still works just as well for clustered BLASs and Mega Geometry, or if a different approach is required.
So the first question was about position floating point accuracy in large worlds, like far from the origin. If you still had to like center the world, like move your origin basically. Yes, the Partitioned TLAS still behaves the same. It's still 32-bit floating point. But this partition translation mode I mentioned can be used to move your origin more efficiently than you can to do today with a full rebuild. So it's somewhat faster. You can also change it on a partition by partition level, so you could also double buffer TLASs. Consumes quite a bit of memory, but it would allow you to, if you only move your origin every 30 or so frames, you can spread out the cost over multiple frames. What was the second question?
The second question was about self-intersections.
Oh yeah, the self-intersection. The CLASs behave exactly the same from this perspective. So all the tricks and things that you did before will keep working just fine.
Great, very easy. Thank you.
Okay, then thanks everyone. And if you have any more questions, we'll be in the front and then a little later outside. Thank you, everyone.